Speed and velocity. Let us start talking about speed and velocity by considering the movement of a particle or the displacement of a particle across a period of time. The speed is defined as the change in distance per unit time. The unit for speed is meters per second. The velocity can be defined as the change in displacement per unit time. The unit for velocity is also meters per second. Notice that the base unit for distance and displacement is meters, and the base unit for time is seconds. So speed is a product of meters and second, as well as velocity. Velocity is also a product of meters and second. However, speed is a product of two scalar quantity. Distance is a scalar quantity and time is a scalar quantity. As such, speed is also a scalar quantity. Velocity, however, is a product of a vector quantity, displacement is a vector quantity, and a scalar quantity, time. Whenever you have a product of a scalar quantity and a vector quantity, the resultant is always a vector quantity. It is worth noting that the gradient of a displacement time graph equals the velocity of the object. Now let's use the displacement time graph to try to explain the difference between distance and displacement. Consider the time periods 0 and 3 seconds, 3 and 5 seconds, 5 to 7 seconds, and finally 7 to 8 seconds. The displacement between 0 and 3 seconds is -6, and that is because we start at our original position and we move 6 meters from that position in a specified direction. The distance covered in that time is simply a scalar quantity, 60 meters. In the next time period, we're starting at 6 meters in one direction from our original position, and we move 10 meters from that position in the opposite direction. Notice that after 1 second, we're back at our original position, and after another second, we're 4 meters in the opposite direction from our original position. The displacement in that time period is 10 meters. The distance covered in that time period is also 10 meters. Between 5 and 7 seconds, we're stationary, so there is no change in position. Between 7 and 8 seconds, we then move back in the opposite direction, 5 meters. That leaves us at a displacement of -5 meters and a distance of 5 meters. To work out the speed, we divide the distance covered by the time taken. So between 0 and 3 seconds, our speed is 6 meters divided by 3, which is 2 meters per second. To work out the velocity on the other hand, we work out the displacement divided by the time taken. In this case, we get an answer of -2 meters per second. Why not try to see if you can work out the values for the speed and velocity between 3 and 5 seconds, 5 and 7 seconds, and 7 and 8 seconds. Now notice that the total distance covered in the 8 seconds of time is 21 meters. However, the displacement, your total displacement after 8 seconds is only minus 1 meters. That means after the 8 seconds, you end up 1 meter away from your original position. That has a tremendous impact on the values of our average speed and average velocity. The average speed will be 21 meters, the total distance covered, divided by the total time taken, 8 seconds. However, the average velocity would be the total displacement, which is minus 1 meters, divided by 8 seconds, the total time taken. Our average speed is 2.635 meters per second, whereas our average velocity is minus 0.125 meters per second. The displacement time graph modeled in this illustration does not reflect what happens in real life. In real life, there is a build-up in your velocity. You do not get from 0 to minus 2 meters per second instantaneously. Instead, you build up velocity or speed until you get to that value. So in real life, our displacement time graph is always represented by a curve. The following example will illustrate that point. Consider a point on a piece of machine that is moving in a vertical straight line. The displacement time graph of P above ground level at a time t seconds is y meters. The graph is shown between the time interval 0 and 4 seconds. Now notice in this case that the curve represents a change in velocity or a change in speed, however you want to think about it. It is not really, it's a displacement time graph, so we're using a product of a scalar quantity and a vector quantity. Therefore, we know that we're talking about velocity, not speed. So we can see that it's a gradual change in velocity throughout the entire 4 seconds. Let us try to answer the questions that follow. Part A. The greater displacement of P above its position when t is equal to 0. At t equals to 0, P is at 12 meters above its origin. It only travels 4 meters higher than that, and that occurs at 1 second. Part B. The greatest distance of P from its position when t is equal to 0. At any one time, the greatest distance of P would occur at t equals to 3.5 seconds. At t equals to 0, it's at 12 meters above its origin. And at t equals to 3.5 seconds, it's now at 4 meters below its origin. It would have traveled a distance of 16 meters. Part C. The time interval in which P is moving downwards. That is simply the time interval between t equals to 1 second and t equals to 3.5 seconds. So our time interval would be t is between 1.0 and 3.5. D. The times when P is instantaneously at rest. Those occur at our turning point in our curves at 3.5 seconds and at 1 second.